Thank you everyone for joining this final session in the openBIM Awards 2024 finalists. We have two categories that we're going to be hearing from the presenters of this afternoon. They are in design for buildings and design for infrastructure. Let's get things started. And the first presentation we're going to hear from is Hugo Silva from TPF Consultores. Hugo, please make your way to the stage, and when you're ready, you can start. Thank you.
Hi, everyone. My name is Hugo Silva. I'm from TPF Consultores from Portugal, and it is here an absolute honor to be here presenting our project of 4 hospitals in Angola. So these hospitals, they are located in different provinces in Angola, and they are divided by 1 multi-story hospital and then 3 one-story hospitals, which these hospitals are very alike between themselves. In these 4 hospitals, each one of them, it has 1 main building and then 10 satellite buildings, and some of those satellite buildings are repeated between themselves. So just giving you some project metrics, it were delivered around 17,400 deliverables, which they are hosted in 376 different folders on the CD. We have 81 native models. In terms of IFCs that needed to be exported and shared, we have 66 different types of IFCs, and IFCs that needed to be shared and delivered to the client, to the appointing party. It was optimized to be reduced down to 35 different types of IFCs. So our design development started from IFCs that were provided by the appointing party. These IFCs had not only the design concept, the geometry and so on, but had all the design requirements that needed to be met for the specifications that the appointing party wanted. So, and from these IFCs, all the task teams could start to work simultaneously without needing that initial interdependence between themselves, especially from architecture, and they work collaboratively directly on the CD. And once the native model started to reach a certain level of maturity, then it was shared periodically. IFCs to be used for many different purposes here on this information exchange between the software. And just here for a quick note, we also produced documents on the Microsoft SharePoint Cloud and then shared on the CD. So this software ecosystem, it is focused on the open standards usage. Of course, then the ecosystem branches to other aspects. So continuing here, the use of IFC from the side of the appointing party, it was used Solibri. That we use not only to check the models, the design progress, the technical solutions that were being implemented on the design, but especially and very important to conduct plausibility takeoffs for cost control. So having up-to-date ICs was something that was really important also for them side. From the side of the appointed party, from our side, it was used BIM Collab Zoom globally, which was widely embraced by all the team members, as it was very easy to use, it was accessible to everyone, and this really empowered the engagement of all the team members independently on their BIM proficiency. We also use this tool to conduct the clash detections, to perform the IFC's quality control. And in some specific cases, we use Navisworks to simulate options to accommodate all the MEP systems inside the available spaces. So this was for technical coordination rounds to see what were the options, so we could put all the MEP systems inside in some spaces that were sometimes not so big. In terms of communication and continuing here the coordination, it was used to BCF in a cloud-based service to communicate all the model topics in the project. And this also gave here another level of collaboration in the coordination management. And there was also this interoperability where one could communicate via different types of software. And BCF, it was used not only for clashes or communicate issues, it was like a standard way of communicate any model-based environment topic. We also used IDS to help us to ensure the compliance of the information requirements on the IFCs as specified on the BP. These IDS rules were set directly on the BIM Collab cloud, where then we could push very easily into BIM Collab Zoom and then run the rules as needed, and then it would automatically identify any non-compliance in terms of information, and then we could easily then communicate via BCF. Here, also in a quick note, and considering here the amount of deliverables and the extensive number of different folders that they needed to be hosted, we used interactive Power BI dashboards to help us to check the quality of the documents on the CDE in terms of their location, nomenclature, revisions, and so we prepared these dashboards based on data extracted from the CDE. And then also prepared some Python scripts to automatically disseminate the documents throughout those 376 folders, and also to manage the revision numbers. Now, talking here a bit about the models and the modeling strategy, and just here for a quick recap. So this project is regarded to 4 hospitals. We have 1 multi-story hospital, 3 one-story hospitals, which these 3 hospitals are very similar. In fact, the buildings that comprise each one of these 3 hospitals are the same, but they are located in different positions. So now we are going to focus on these 3 hospitals, although the 4th hospital would also follow the same principles, since some satellite buildings are also the same. Okay, so coming back to the 3 hospitals, as we can see here on this image highlighted in red, we have the building 04 that is repeated 4 times. And highlighted in blue, we have the building 01 that is repeated twice. So each hospital, it has 11 buildings, but in fact it has 7 different types of buildings. So in order to optimize here the design production, it was modeled only the 7 buildings separately, and then it was used, these models and the prepared views, to be reused across the 3 hospitals in aggregated models. This really prevented a lot of work repetition and gave here another efficiency on the design production. But this meant that we needed to export 33 IFCs per discipline for the 3 hospitals. From the side of the appointing party, they were not welcoming very much receive this amount of IFCs, and also from our side, the appointed parties, we were also seeing that this was not very efficient. So it was prepared Python scripts with IFC OpenShell library that enabled us to only need to export the 7 IFCs, and from this we could generate 3 federated IFCs with 11 buildings each, or in other words, from these 7 buildings, we could generate 33 buildings divided by these 3 federated IFCs. And explaining just a quick, the workflow of this script. So from these 7 exported IFCs, the script copies those IFCs and makes the necessary duplications for those buildings that are repeated, the building 01 and the building 04. Then it adds a prefix in the file name identifying the building, which that information is then used by the script to make the changes that we want through dictionaries. Then it conducts several changes, such as the IFC building name, the location of the IFC building, and so on. And once we have that information organized in these temporary files, then the script generates an IFC, an empty IFC, and merges and collects all the data into this IFC, and restructures this IFC in order to have all the IFC buildings associated to a single IFC site, which is used as reference, the first model of this list of the temporary files. It is always used our reference model. It changes the name of the IFC site and then removes the remaining IFC sites and IFC projects. And then finally, it eliminates the temporary IFC files. So here, just to give an example, here we can see here an IFC structure from an IFC generated by the script. We can see here the several IFC buildings allocated to an IFC site. However, then it was reported by the appointing party that authoring tool that they were using, the version of the authoring tool that they were using, could not import more than one IFC building per file. So he requested for the disciplines of architecture and structure to submit IFCs with a single IFC building. So we made here a script variant that would relocate all the objects to the IFC building story of the first reference model, the corresponding IFC building stories. So, and just here, explaining a bit here the principle of the script variant, and also here for the sake of sharing. While before we were focusing on the IFC role aggregates to associate the IFC building to the IFC site, here we have the IFC rel containing special structure that makes here the association of the objects to the IFC building story. And considering here that the relating structure name is associated to the name of the IFC building story, basically what this script does, it searches through loops the relating structure names of all the IFC rel containing special structure, and then relocates to the correspondent IFC building story of the first reference model. And then at the end, it removes the remaining IFC buildings and the correspondent IFC building stories. So here, to wrap up, well, besides here the obvious interoperable advantages of using open standards, we also witnessed that they are really easy to use. They are accessible to everyone. And this really empowers here the engagement of the team members independently on one's BIM proficiency. Specifically here, the IFC format, well, it made it possible for us to use Python scripts to improve the efficiency on the model production and delivery. And it has also shown to be a very flexible and reliable solution to deal with specific challenges that sometimes arises on the projects. So we believe that in this project, it is just here another testament of the incredible potential of openBIM in AEC projects. I want here just to address to those that were involved in the project, and I want to thank you all for your attention.
Thank you very much, Hugo. Next up, I would like to invite the team from Hing Engineering Company Limited to the stage.
Good afternoon, ladies and gentlemen. My name is Simon Lee from Kai-Tak Sports Park Limited. I'm also a director of Hing Engineering. We are deeply honored to be here today to share with you Kai-Tak Sports Park, an integrated sports, cultural, and entertainment facility in Hong Kong. The sports park covers an area of 28 hectares. It is part of the redevelopment of the former Hong Kong International Airport in Kai-Tak. The park is a design, build, and operate project, with Hing Engineering being appointed to take care of the design and construction. The park features a 50,000 capacity main stadium, an arena for sports and entertainment event, as well as a public sports ground, together with extensive public open space for the public's enjoyment. This is a huge complex. Without the adoption of the openBIM approach, it is almost impossible to complete this project within just 5 years. A project at this scale and complexity requires lots of expertise. The team managed to gather 500 beamers from all around the world, working as one team. At beginning stage of the project, Hing managed to train and form a beam management team of 50, which helps to complete the project as we move on. Now I'm going to turn the stage to Nathan, who will tell us more details. Thank you, Nathan.
Thanks, Simon. Hi, I'm Nathan, a principal at Populous, the architects on this project. Our main design vision here was to really integrate the project into the very fabric of Hong Kong. This needed to be a community hub and something that would benefit the public, but we also wanted to inspire current and young emerging athletes living in Hong Kong. The magnitude of this project was quite enormous. It's 800 uniquely authored BIMs. We had over 5,500 IFCs exchanged and over 85,000 BIM track issues resolved using the BCF format. This was 140 global companies working together. And crucially, the Hong Kong government on day one said to us, one of our key goals is to maximize the use of the BIM on this project. That gave us the mandate to really set out a very clear virtual design and construction strategy for everybody involved, which was crucial to getting this done. We generated over 158 million square meters of the surrounding Hong Kong context. GIS was used across the various sources of models to align all the models and to also check and validate their location proximity, cross-referencing that against the project BIMs and also all of the project surveys that we had. This process involved using digital maps, terrain data, open source data, and also privately sourced context models, which we then compiled together using all of the embedded GIS data in those files. After that, we went and used photogrammetry to make sure that we had a higher level of detail for the site and make sure that we had all of the latest information that we needed. These videos are created in Unreal Engine 5. We've directly translated the BIMs across to the engine using DataSmith and Data Prep. Okay, so the facade rationalization of the main stadium. This is one of the most complex parts of this project. What we needed to do was actually align our design vision with the practicalities and the feasibility of actually getting something of this size manufactured and installed on time and budget. We knew we needed to iterate very rapidly, and the only way we could do this was with very early subcontractor engagement with the manufacturers so that we could exchange BIM models in a bi-directional flow so that we were working on the design models. We could share those models direct to our subcontractor who could then analyze what was happening, send it back to us to make sure that we could actually make this work. This virtual collaboration, had it not happened, would not have allowed this to be possible. One of our main design drivers as well was to minimize the amount of material wastage when cutting the panels. This is a brief overview of our facade rationalization workflow. A lot of coding, a lot of visual scripting programs, and then again, the bi-directional sharing of models between ourselves, manufacturing and engineering. So the digital process here is really about rationalizing a few key points to the project. The first one, rationalizing the panel vertical grid spacings between each panel. We need to make sure that we are mitigating the amount of bespoke panels that are being used. We need to maintain the fixing details of each one. And we want to make sure that we're flexing the panel gaps enough to get our design outcome without it impeding on the installation of the panels. Arup and Populous also worked very hard on and rigorously on our glare analysis to make sure that the panels were not having a negative imposition on the nearby residents of Hong Kong. So ultimately, we actually, through these virtual processes, we've reduced our panel count from 47,000 to under 27,000 panels. We've managed to reduce our overheads in construction, particularly fabrication and installation, by 40%. We've reduced our steel tonnage. We've reduced our glazing weights. And incredibly importantly, we've actually reduced the CO2 emissions of our facade by over 25% on the main stadium and over 30% on our other venues. I'd also like to take a quick look at some of the other work we did focusing on our spectator analysis and experience when designing a venue. So we're specialists of stadium seating bowl design. Really, the main drivers for this are the fan experience. Our main goals here are to make sure that every fan can see the field of play well. We want to make sure that they don't have any obstructed views, and we want to make sure that their proximity to exit points and also to amenities is optimal. So, 2 primary goals in this process. To do this quickly and to make sure governments and clients are happy with the results, we needed to create our own series of workflows and tools that could work alongside the main authoring platforms. And we also needed to make sure we had a way to easily validate every step that we took and every design change that we made so that our contractors could understand and know that we were making the right call with every decision that the team made. A quick look at our design analysis workflow. The main point here is really getting the information out of the models and the data out into Power BI or Kibana or Tableau in order for our stakeholders to be able to visually understand what was going on so that they were happy with it. This is a quick look at one of the new platforms we built, or a custom-built software to enable us to quickly iterate on what we were doing. openBIM is critical for this, the concept to allow us to do better stadiums and actually create new benchmarks. We need to create new software and tools to be able to work for our specialization. It's critical when doing this that we can allow the geometric and non-geometric data to flow throughout the entire ecosystem and not be bound by a particular software platform. So that's a small sample of one of the platforms we built for this project. So some of the key objectives that we achieved from this. Well, firstly, how do we measure this? There's quite a lot to go into here and it's complex, but at a very basic level, we use a range of qualifiers to actually validate and judge the success of a seating bowl. What we're looking at here is C values, and C values tell you how well a fan can actually experience an event. We generated a minimum of C value 75 for our general arrangement and 125 for our VIP suites. That's actually really a new benchmark in rectangular seating bowl design throughout the world. Thanks, everyone.
Okay. Thank you, Nathan. I'm Horis from Arab, and I will continue to discuss the application of openBIM in this project. So first, it's about the mass motion analysis. As mentioned earlier, Kai Tak Sports Park, it's uniquely located in the heart of Hong Kong city center. The central location makes the design of the crowd dispersal very important. Our goal is to ensure that 50,000 attendees can arrive and leave the venue smoothly, avoid congestion both inside the venue and the surrounding public transport network. And to achieve this, we have to carry out detailed mass motion analysis to simulate the crowd dispersal under different event scenarios. Mass motion is an OASIS software which is compatible with IFC, which can seamlessly integrate it in our BIM workflow. Our workflow involved is we first extract the useful information in IFC format from our BIM model. Then we import it directly to mass motion software. The key elements such as the staircase, the escalators, or the barriers will be imported seamlessly to this model so that we can quickly set up the mass motion analysis. With the detailed mass motion analysis, we can simulate various dispersal scenarios for 50,000 attendees, ensuring them they can merge into the nearby public transport within 60 minutes after the end of each event. Next, I would like to mention about the CFD analysis we carry out. CFD analysis is very important for sports facility design, which helps to verify the airflow and also the thermal comfort of the audience. Our design workflow involves the extraction of useful information in IFC format, and we tidy up these IFC files by our script in Rhino and Grasshopper. Then we export the files to make the final element model for the CFD analysis. With the use of the openBIM workflow, we can quickly set up over 20 CFD analysis model to test the 20 different operation modes of the stadium and also the main game arena. Particularly for the concert mode in the main stadium, which over 10,000 audience will be in the pitch area. The CFD analysis help us to verify our design assumption for the pitch cooling and also ensure the thermal comfort can be achieved. Let's move on to the steel roof design for the Kai Tak Stadium. The Kai Tak Stadium features a very unique roof design that combines the fixed and retractable elements. So early in the design phase, Populous and Arab has already made use of openBIM to exchange design information, which enable a quick adjustment of the design. The whole design will be in a parametric environment under Rhino and Grasshopper. And then we make use of the structural software to carry out the steelwork design and the steelwork optimization. The structural information and the necessary adjustment will be documented in the IFC and communicated back to Populous for the necessary adjustment of the architecture design. So these workflows actually will go on until certain level of maturity has been reached. So this is the overview for our overall roof design workflow. Once the design is mature, we will set an federated BIM model for us to directly communicate with the steelwork fabricators. We actually developed a Grasshopper script for us to quickly verify the accuracy of the fabricator's model. The as constructed information can also be imported to our BIM model by means of point cloud data. Lastly, I would also like to mention that sustainability design has been deeply embedded in this mega project. We have secured 3 green different certifications. One is BIM Plus Platinum, LEED Gold, and also the China 3-star Green Building certifications. We also make use of openBIM workflow to help us to achieve the sustainable design in terms of carbon life cycle analysis, the glare analysis, and also the CFD analysis. Lastly, we also fulfill these kind of sustainability design goals. Now I'll pass the time to Billy.
Thank you, Horis. So for this open collaboration, we are heavily using a lot of openBIM, OpenGIS, and OpenCDE concept. By utilizing BCF, we can synergize all the software together. And this is our CDE ecosystem map. By utilizing the OpenCDE concept, and you can see we know that the whole life cycle, different phase may want to use different CDE. Say for example, designer want the Autodesk BIM 360, and the contractor want to use Stylus. And it's just similar as the ISO BIM 19650. And as a result, we are using more than 200 models being collaborated bi-weekly, speed up by 3 times using BCF format, and digitally signed off using IFC for our sharing, archive, etc. And it also helps us speed up 90% for the reporting and the communication. And also for the Solably, we utilize this, and we have more than 30 rules was implemented and speed up our time, our engineer for 20 times for their engineering works. It helped them saving a lot of time for their engineering tasks instead of checking. And also the architecture part, they also are using AI help us to speed up for the wall fixture coordination. It speed up from 18 months down to 6 months to finish the work by thanks for the IFC standard, data standard, and the AI automation. So we don't need this kind of drawing anymore for our switch layout design, drawing one by one. And this is our achievement. We have a good interoperability for collaboration, speed up the fabrication process, tackling site issue earlier before the design frozen, and also allow us to use best-in-class openBIM tools to do the right thing with the right tools at the right time. And for our lesson learned, I think this is our vision for the next mega project. Client side should be contractually buy with IDS and BSDD standard. By utilizing IFC and BCF workflow, we can collaborate all the professional software together, and hopefully we can do a better, faster, and smarter project next time. Thank you.
Thank you, Billy and colleagues. And we will move on to the 3rd presentation in this category from Kontrast AB, Hanif, Erfan, and Sandra making their way to the stage.
Hello, everyone. My name is Sandra Azadi, and I am here today with my colleagues Hanif Pourghazian and Erfan Samadi, and we represent Kontrast. Kontrast is a multidisciplinary office working with architecture, digitalization, and project management. Here you can see some example of our projects. We are located in Stockholm, Sweden, but we are active internationally as well. Our goal is to work with projects with high design ambitions. We like challenges, and that's why we prefer to work with large-scale complex projects where strategic thinking is required to add value and where we find the opportunity to evolve as a company. The project we are going to look at today is an office building in Stockholm, Sweden. The project consists of 30,000 square meters of office, conference, and event spaces, and was finished in 2024. We would like to present the project with a short video clip.
Vi ska då prata lite om Origo, som då är kundgårdens senaste byggnation, nyproduktion i Solna. Där vi har varit med och utvecklat sedan 2008. Vi har ett stort bestånd av fastigheter där. Vi har försökt skapa en produkt som ska attrahera en framtidens arbetsplats, kan man säga.
Jag tror att stora som det var att vi vågade vara annorlunda, vi vågade ställa vissa krav, vi vågade ställa krav på att man skulle inte samma plattform. Och kravet var att antingen så gör vi det också så är vi
really interested in doing this project for 100% real estate or 100% 3D estate. In those days, we are really that okay, it's not possible to make 100%. We don't limit until 100%, we won't get as far as we want.
So the client had high ambitions, but there was also a need for increased structure and control of the project. The contract form was a so-called CM build contract, which implies that the client is both the appointing party and the appointed party according to ISO 19650. A construction management company was hired to help the client to develop the request documentation. The same entity was then also the receiver of the request documentation as the appointed party. The project is divided into a large number of partial contracts that are procured separately and managed by the CM company. This model is often used by large commercial projects since it gives the opportunity to change the project at a low cost. Commercial projects have a strong need to adapt to market circumstances. In our case, since the start of production, we had an unforeseen pandemic. We had the Russo-Ukraine war with delivery shortages. We had an rising inflation, surprisingly, and radical change in work behavior, which led to insecurity in the office market. So all these factors led to the fact that the building changed shape from this into this. So it goes without saying that when 150 separate contracts are managed at the same time that the building is changing shape, requires good tools to maintain control. The project in total changed the scope about 19% during construction, but we managed to maintain the adjusted budget increase to around 0.5%. So when we entered when we came into the project, there was a 3D model on the side with restricted access and used mainly by the design team. There was also a large number of different platforms used for different parts of the project, such as a cloud storage for drawings, client's own document storage, CM company's document storage, separate platform for model task management, tons of emails, separate platform for viewing 3D models, an external software for 2D reviewing, and meeting protocols in various formats. We wanted to change the 3D model and place it in the center to use as a communication tool. Then we wanted to include everything in one CDE so that we could obtain overview and better control during the project. The centralized CDE platform is our definition of the digital cocoon. So in the start of a project, you never know how the project will evolve. Therefore, it's very important to design the CDE so that new processes can be added when the need arises. There are multiple processes that work simultaneously in a project. Each process is linear, but the project as a whole is seldom linear. Take the design process, for example. It starts off with a client request, which is elaborated by architectural and technical consultants. The proposal has then to be reviewed during a review process before it's finally approved and can enter the next phase. Since all communication is made in the digital cocoon, all the information comes from there, and since all data is stored in the digital cocoon, the results are sent back. This can be visualized like this. So, information comes from the cocoon, is processed, and the results are sent back to the cocoon. Various other processes can be added in the same way, where information is collected, processed, and sent back. So as time goes by, the amount of information is increased and new processes can be added, such as the process for sustainability, simulation and analysis, model validation, budgeting, economic prognosis, and procurement. When procurement is done, contractors will be added to the CDE, and there will be a need for a separate construction model. This model contains only the parts of the building that are approved with construction documentation. So from the beginning, the construction model contains only the foundation and gradually is completed with other contracts until it reaches the same level as the design model. When construction work starts, there will be need for new processes, such as the process for inspection and change order. When we look at the process map, we can see that the left side is focused on design processes, whereas the right side is focused on construction. But they are all connected to the same core and can influence each other as parts of one whole. This this type of communication, this kind of digital communication and data storage is possible thanks to the openBIM standards. So when we look at the process map with BIM glasses, we can see how different hardware and software can communicate with each other seamlessly. When the project is finished, is the construction model that is more complete, and the design model is not necessary anymore and can be archived. The construction model contains all the correct information of the building, so components can be changed into assets, and the CDE can be used as an asset management tool ready to be handed over to facility management.
Thank you, Hanif. It might be interesting for all to see how these theories turn to daily practices. In next video, we are going to watch some supporting evidences.
By and GIS standards, we placed a point cloud model with less than 5 centimeters error, capturing precise details of the surroundings.
By linking door cards to construction plans, we sped up the review process and newly eliminated mistakes in door production.
All reference and detail drawings are linked, so there's no time wasted finding them, and everyone always sees the latest versions.
All 2D plans, roof, and floor drawings are automatically scaled and linked to the CDE platform during export, greatly aiding coordination meetings.
We have about 100 fixed stations inside the building, taking monthly 360-degree pictures that save significant time and cost during online design meetings.
All meetings were scheduled inside CDE, with minutes linked to 3D with VCS, making navigation to the relevant areas easy during meetings.
All consultant IFC models are overwritten with each export, enabling model comparison and change control.
VCF communication significantly reduced time for review, flash control, and model validation, leading to more accurate and optimized production.
All communication with tenants were handled inside CDE, allowing tenants to participate in the design process and view their spaces in 3D.
All inspections and safety rounds were conducted in the CDE platform, with inspection points linked to the model geometry and sent via VCF to the responsible person.
All rooms and zones are exported to the CDE, containing key details like specification, geometry, and sensitive information useful for building maintenance.
The entire procurement process was managed in the CDE platform, with the help of given quantities from models. We could ensure accurate cost estimates and budget planning.
Change orders, time planning, and budgets were managed in the CDE, with 3D changes linked to models for clear understanding by all parties.
Production people on site have access to the exact same IFC models as clients behind the desk.
All digital information is reviewed by all parties and ready for construction.
Consultants had to deliver according to IPM, MDD, and BSDD standards. All object parameters will be handed over.
Well, that was cool BIM features, right? Let's take a look at some numbers from our design process. We had more than 600 direct users inside the CDE platform. We had 27 IFC files, which were constantly updated with almost 255,000 IFC elements. However, we had only around 800 clash detected and solved, which is not much for that many elements. Well, the reason is nothing but collaboration of all parties in one CDE platform. During the course of the project, over 6,000 tasks were issued, and we had also more than 3,400 comments. Some of these comments were created during our design review processes. We had 68 packages for reviewing different stages of design. So in total, we had close to 10,000 communication threads inside our CDE platform. These are legal references and which can be easily filtered and sorted out for future use.
Summarize it, the centralized CDE platform gives us the advantage of keeping control in stormy waters. The time for communication and finding information is reduced substantially, so you can just pick what you need. There's no need to send a request for information. It also gives increased traceability, which gives enhanced accountability, and this results in user taking more responsibility and raise the level of quality control for their deliveries. And this creates a sort of digital lean production. So everybody, from the workers on site to the project manager behind the desk, uses the same model. This leads to equality and higher engagement, and with all information stored in the same place, it results in a collective memory of the project. So now we all strive to work hard to advance in the field of digitalized construction with CDE platforms stored in one openBIM standards and AR futures, and then we come to the work site and find this on the wall. So it's a printout of the CDE used by the workers change is good, but we also need to know that there are people who need more time, and we have to help them on that way. Thank you very much for your attention, and sorry for the extension of the time.
Thank you. So if I could ask Hugo and the team from Hing to make their way back to the stage. We'll just take the time for a question to each of the submissions before we move on. Same question to each of them. Yeah. See what they come up with. Yeah. I'm in favour for it in the interest of time as well.
Oh yes, I mean. Yeah.
Okay, I'm going to hand over to Nick, who has a question.
I'd like to ask each of the finalists what lessons or changes would they take forward to their next project, given their experiences?
Especially this part of manipulating the IFCs, this was something a bit new for us. We still see a lot of field to develop on that side. In this case, in the example that we had the repeated buildings, we had to change the UIDs. In this case, we'd like to have a JSON workflow that we could store those UIDs, so we could not to maintain the same UID in the final delivery. That would be an example. And also in the removing the IFC project and the IFC site. Well, when we did that manually, changing the TXT files, it went okay in the validation service on the available on buildingSMART. With IFC OpenShell, we would need an extra step to not have problems of syntax of remaining IFC rel defined properties and so on. So it would be like technical things here on the IFC.
Thank you. Same question to one of the other teams.
Actually, today morning I did present one about Rugby 7 slide. I would say at the very beginning, if a project not set up good enough IDS and BSDD, I think we would like a game, like a Rugby 7, but without rule and policy. So everybody just fighting together, then try to align what is the regulation, what is the workflow, blah, blah, blah. Indeed, in our project at the very beginning, we have this kind of a short period to align our expectation and the workflow. It would be great if for next project, if we set up the IDS and BSDD, as I mentioned, this should be, openBIM should be a mandatory and should be contractually binded. Then everybody has to follow. They would notice that this is the requirement, and they will more eager to start understand what is openBIM is about, how to work early engage with subcontractor, how to do using openBIM workflow to smooth line all the information, to standardize the data, etc., to make our life easier, to run the process more smooth. Yeah, that's our lesson learned. Yeah.
Thank you. And finally,
yeah, we would like to use a CDE platform that is even more open. Many of the CDE platforms that can be used today are good, but they all have their restrictions. This would give us the possibility to be able to add even more processes, because we see a great value of having all the project, all the communication, and all data in one platform. So with even more open CDE platforms, I think the success of this centralized CDE would be even more.
Thank you. All right, we have run out of time, so the decision was made to ask the same question to each of the teams. So thank you for your answers. We will move on to the final category of the day. If you could please vacate the stage. So we move into the category of design for infrastructure, where we're going to hear from two different projects. First up, I would like to invite Huaisong, representing China Railway Eryuan Engineering Group Company Limited.
Good afternoon, everyone. I'm Huaisong from China Railway Eryuan Engineering Group Company. And our submission title is Application of openBIM in the design and delivery of Guiyang to Nanning high-speed railway. And now I will introduce our project from the following 4 parts. They are project overview, ISO 19650 used, openBIM used, and benefits. The first part is project overview. Guiyang to Nanning high-speed railway is one of the key parts of China's 8 vertical and 8 horizontal high-speed railway network. The total length is 482 kilometers, and the design speed is 350 kilometers per hour. Total investment is $10.4 billion. And this project started in 2016 and has been put into operation since 2023. And this project has high requirements on quality, safety, environmental protection, and sustainability. This is regarding the party and the stakeholders. The owner is China Railway Nanning Group, and the design company is China Railway Eryuan Engineering Group Company, and the construction company is China Railway Electrification Engineering Group, and the platform provider is China Academy of Railway. And we have summarized the 4 highlights in this use case. They are process, platform, standard, and software. Process means ISO 19650 standard process and openBIM based engineering and production process. Platform including BIM and GIS and the digital delivery platform. The third is standard. We have produced the object types, pieces, BSDD, use cases, IDM, and the conceptual model for IFC rail. And we also completed verification and validation of IFC 4.3. The fourth is software. We have developed different kinds of modeling and simulation software in this project, such as parametric rapid modeling, single variability check, and video coverage simulation, and so on. The second part is ISO 19650 used. In order to achieve a better information management process, at the very beginning of this project, we adopted the ISO 19650 standard. And firstly, we extracted the information requirements from the contract. And the left shows the signature of the stakeholders, and the right shows the main requirements from the owners. According to the requirements of the owners, our main goal of this project is to realize an in-depth application of openBIM and the digital delivery, and then improve the information, digitalization, and intellectualization of this railway. So in order to carry out these requirements, we adopted ISO 19650 information management process and produced the BEP, fully adopted openBIM standards such as IFC, IDM, BCF, and MVD. We also established the project CDE to realize the cooperation, data transferring, and the sharing. So in ISO 19650 process, the core process is from appointing parties and then produce information requirements, and finally completed the information model delivery. And we realized the data transferring and sharing from design to construction in the process of construction and by CDE platform. And this slide shows the responsibility matrix of this project. And we also produced the OIR, PIR, EIR, AIR according to ISO 19650 standard. We also developed a BIM execution plan as well as the associated milestones in this project. We have regular meetings, trainings, as well as on-site surveys in the process of our project. The next part is CDE. We built a CDE platform that integrated different kinds of software, and this platform meets the collaboration needs and ensure that BIM information data can be lossless transmitted and shared in the design and the delivery process. The third part is openBIM used. This slide shows the software ecosystem map based on BIM, openBIM, and ISO 19650 standards. We use the different software in the project. For example, we use ProjectWise for collaboration design management platform, AutoCAD and ORD for alignment design, ORD and MicroStation for the design of bridge, tunnel, subgrade, signaling, and so on. And Revit is for building design. And RealWorks is as CDE and the BIMGIS platform. And in the design and the delivery of this project, we use the exchange formats such as IFC, QB, BCF, XM. We have 5 key use cases in our project. The first, now I will introduce these use cases. The first use case is cloud-based component library, and we have built a cloud-based component library that covering railway domains. And the second use case is BIM and GIS. We created a BIM and GIS platform, and it integrated display of the entire railway line and help with the multi-domain solution reviews based on BIM and GIS. And in order to efficiently and scientifically determine the railway alignment, we also developed an intelligent alignment selection system based on BIM and GIS. The left shows the intelligent alignment selection system, and the right shows a comparing between intelligent alignment selection and manual alignment selection. And the third use case is 3D collaboration design. And this picture shows the 3D collaboration design of signaling, telecom, and energy domains. And this is the 3D collaboration design of alignment, subgrade, bridge, tunnel, and the station buildings. And this is an example of point machine and signal collision detection and design optimization. As we know, there are some hidden areas in railway engineering, especially the underground cables. So we use 3D models or VR to help the workers to locate the hidden facilities. And we also use visualization and VR to help with the training and safety management. The fourth is simulation. And as I have mentioned, we have developed different kinds of simulation software in our project, including video coverage simulation, single availability check, railway clearance detection, and construction process simulation. The last use case is digital delivery. is a very important use case in our project. In order to implement the digital delivery, the project built a platform based on RealWorks, which is a self-developed platform. And the delivery file formats include IFC, XML, PDF, etc. This platform realizes lossless transferring and sharing of the information. On the top right corner, this picture shows the comparing of information transferring between digital delivery and traditional delivery. And we adopted the international standards such as ISO 19650, FC 4.3, as well as CRBIM standards. We have produced the PSETs use cases, BSDD, IDM, and UML for IFC Real extension. And we also completed the verification and the validation of IFC Real. And the outcomes have been included in the officially released ISO 16739 standard. The last part is openBIM benefits. It can be seen from these statistics. We have 19 software, about 100 PCF topics, 36 FSVL extensions, 457 entities, nearly 700 pieces, about 380,000 objects in this project. Regarding the economical benefits, first we reduced the number of alterations by 50, and the construction period was shortened by 35 days. Total cost reduced by $2.75 million. And we also effectively avoided about 100 cases of errors or mistakes. And we improved the efficiency of modeling by more than 30%. And the technique clarification efficiency increased by 50%. And the training time reduced by 50% as well. So in addition, the design review platform not only improved the review efficiency by 30%, but also reduced the travel cost by 25%. BIM and GIS achieved low carbon alignment design, which reduced 70 carbon dioxide. The digital delivery platform achieved a paperless process. And this is application proofs from different stakeholders. And this slide shows an overview of benefits. There are some keywords in this slide, such as quality, efficiency, optimization, cost saving, and real-time data sharing, and sustainability, and so on. So to sum up, thanks to openBIM solutions, not only the project objectives and budgets reached the expectations on schedule, but also the digital delivery was implemented. These achievements not only greatly improved the quality of the project, but also reduced costs and risks effectively. That's all. Thank you for your attention.
Thank you, Huaisong. And the last but not least presentation of the day, I'd like to invite Copenhagen Metro to the stage. Thank you, Esther, Boriss, and Elvinas. Just getting your slides up. And when you're ready, please, you can get started.
Good afternoon. We are Copenhagen Metro. My name is Esther. I work as a BIM manager in the company, and today with me, my colleagues, Boriss, who is an application engineer, and Elvis, who is a BIM coordinator. We are responsible of implementing openBIM in the company, and today we are presenting the openBIM integration and data validation in conceptual design phase for the new M5 Metro line. Copenhagen Metro was established in 2007. Currently, we have 4 lines in operation. The company responsibilities are developing and building the metro system in Copenhagen, Denmark, and enhancing the customer experience to support the city mobility and environmental goals through innovative solutions. As a client, we have a high ambition of implementing openBIM. For that reason, we have set 3 main goals. The first one is to overcome boundaries of interoperability and to never be limited to a specific softwares. The second one is to have a standardized and structured data to increase data reliability, automation routines, and to help us to take data-driven decisions. And the third one is to have a CDE aligned with the ISO 9650 that can support open collaboration and ensure that all the information related with the project has been shared and coordinated across all the stakeholders. In Metro, we have set an objective of implementing openBIM from initial phases of projects to support our business needs. To achieve that, we have started the openBIM standardization project, which a roadmap is presented on the screen. Going from left to right, we have started researching, testing, and mapping our OIS, that is our internal classification system, with the IFC 4.3 schema, as well as standardizing our parameters and providing it through the attribute matrix. Then we move on to build our own database to provide our data through BSCD to externals. Then we deploy our IDS for the model review and shared the inconsistency through BCF and ACC, that is our common data environment. The new M5 Metro line will be located in Copenhagen, Denmark. The project consists on 10 stations, approximately 12 to 14 kilometers of double tunnel, 5 kilometers of elevated track, and an artificially created island. The opening plan is expected in 2035, and the phases of the project consist on conceptual design, reference design, then we go for tender, then we have preliminary design, detailed design, and construction. Currently, we have finalized the first phase that correspond to conceptual design. Some of the most important requirements of our EIR are that we want all the work to be centered in our CDE with the IFC as a primary exchange file format. We want the OIS, our classification, to be integrated with the IFC schema and its domain. We want all the parameters presented in our attribute matrix to be embedded in the model. And our main vision is to have the IFC as a base for all the BIM uses workflow. The project organization consists on multiple projects. Some of them are presented on the left side of the screen. And on the right side, we can see an illustration of the flow of the information in our CDE that is compliant with the ISO 9650. For conceptual design, we have received 116 IFC file, which combined form 30 federated model with around 57,000 objects presented. The review process consisted in 2 rounds where we checked the OIS codes, the IFC types, and the parameter requested for that phase. We have provided 30 class detection report and 30 data checks report. An average of 94% of the data has passed our checks.
To have a good schema, we had to standardize our data. That meant mapping our OS classification system to IFC and also refining it so it works better with IFC, because we did not want OS to simply replicate what we have in the schema. Instead, we wanted it to complement it and provide additional information. That meant dealing with a lot of data tables and a lot of mapping tables, and looking at the size of the data and the amount of users involved that it would take to maintain this data. We decided to opt out from using Excel, and we moved this information to a database. So we've created a SQL schema, we've normalized it, and we pushed all of that data into that database. So that became our single source of truth. One very important thing that we were able to do with this is that we were able to impose constraints on this data and not allow people to type in things that they're not allowed to type in. So for instance, if one table depends on another table, then the user needs to update both tables. Otherwise, the system isn't going to allow him to do it. Or if he needs to insert a 3-digit code, then he won't be able to insert anything but a 3-digit code. Next slide. So in the middle, you can see the schema. And we only work in the database. The spreadsheets are only used to export that information for documentation purposes, and then that would be shared with our consultants. The exports would happen either on a schedule automatically or on demand when it is required. Having this information embedded by our consultants in the model creates a lot of consistently structured data, and we can build on that, and that unlocks a lot of possibilities for us to use that data to inform our BIM users. And we don't have to worry about fixing issues and trying to manually digest these inconsistencies once we get that data. So we don't have issues like attributes not named consistently across contracts and stuff like that. Next slide. We did not want to use spreadsheets to exchange this information, of course. We wanted to use BSDD instead. The API provided a lot of possibilities, both for us and for our consultants to utilize this. We did play around with it. We created a test domain, I believe it's called in BSDD terminology. We loaded our database data to that domain. But this was a live project. And stage 2.1, 50% was looming. And it was very important for us to make sure that the requirements that we've provided to our consultants are actually embedded in the models. And we wanted to have a workflow that is already tested, deployed, and that we could improve and then go into future stages with something really solid. And that's why we jumped in straight to IDS checks.
And we looked into standard IDS workflows and procedures and started to create a workflow that would help us implementing it in our CDE. IDS allowed us to check and validate our requirements using open source packages. As an example, we used Blender BIM plugin in Blender software and worked on custom scripts to fit our needs. And we created an automation routine to generate IDS file from our database to make sure that the requirements are up to date, allowing us to skip the manual part of creating the IDS file manually. Even though we have automations, we still needed to manually run scripts in a set sequence, as well as running every model individually, which consumed some of the manual work and took some time, and we wanted to improve on it.
On the top right side, you see a diagram, and you have we have two verifications that are running in parallel, essentially. The top one is the IDS verification, and the bottom one is the verification that we've built ourselves with IFC OpenShell. That we've built to overcome the limitations that we've encountered with the IDS verification. This resulted in a fractured workflow that was semi-automated and that also produced fractured output, which were HTML reports from Blender and CSV reports from our own IFC OpenShell checks. Next slide. So we weren't exactly happy about that. So we decided to create our own solution and to automate the whole process. So what we've done here is that we made all of these automation routines or script execute in a predefined sequence where output from each script serves as input for the next one. And we have almost 100% automated solution here. And it is actually pretty straightforward. On the top side, what we did with Blender is that we altered the way that Blender BIM works. We altered the code behind it and some of the packages that it uses. We've rebuilt that, and we made it iterate through the folder structure that we pointed to, detect all the models there, and iterate through the models one by one and execute the checks automatically, produce the output. At the same time, our OpenShell workflow would do the same in parallel, and then this data would be combined automatically into a single output. That is a CSV report that you see right there, where we do some color coding, and we would automatically generate dashboards to visualize compliance per station and per section as well. We wanted the solution to be user-friendly, so what we did is that we took a single Python executable that a user needs to run. He literally needs to double-click on it, and that will initiate this whole process. What the user needs to do, though, is he needs to update a settings file that contains directories to indicate where the models are, where the output should go, some of the installations as well. And the last thing to note, I suppose, is the fact that after these reports are generated, this routine automatically places them in the correct folder, in shared, in ACC, through desktop connector. And this is just an overview of our ecosystem that is very heavily based on ACC. These are some of the things that we specifically used for the openBIM project. So we've got MySQL, we've got a bit of Workato there, we've got IDS as well, and all that output goes into the shared folder and subsequently gets moved to published when it gets picked up by our consultants.
So here we have the openBIM strategy roadmap for the following 2 years. And it presents the goals for the second part of the openBIM project. And some of them are, the first one, we want to expand our OIS classification system to ensure compliance with the IFC schema. Number 2, we want further improving our database to support and communicate or inform our BIM users. Number 3, we want improving our BSDD integration with our database to efficiently share our data with externals. Number 4, we want to overcome limitations of our city by using BCF and promoting openBIM communication. And number 5, we want to continue improving our IDS workflow by emphasizing on data visualization and, the most important, keeping the solution user-friendly. Thank you for your attention.
Thank you very much. So if you could remain there on the stage, and if I can ask Huaisong to join you.
What improvements to the buildingSMART offering would support them? You know, what do they need from buildingSMART that they haven't got yet? I have a feeling that Copenhagen is well into it, but the Chinese project is a little bit...
It was more ISO focused, it was process focused.
Yeah, I'm not sure I believe everything. So, well,
feel free to. Yeah, feel free to. No, you're fine. Feel free to ask a question.
What do we
You can ask a question.
What could buildingSMART support them there?
Okay. Great job. Thank you for your presentations. We're going to do the same, ask the same question, and if both teams could respond. So what improvement would you suggest to buildingSMART on open standards and or even the ISO implementation? Any improvements that you'd recommend?
Okay, well, in this project, and we just use some like the ISO 19650, and also some new technology about the CDE and BSDD, and this technology, all this some really helped for our project, and especially from the design period and also delivered to the construction period, and also in China Railway domain, we have many. Also in the design period, we also have many stages and also has different measures. And also it seems like the alignments and bridge and building and so many domains, and we need to combine them and to do the whole design procedure and to combine these different domains and then to create a complex construction. And also it's need to use the BSDD and the CDE to have and also we just developed a system by ourselves, and we can just deliver these digital assets and from the design period and to the construction period, and it's very efficient and also can solve the many problems like the data that we maybe in the traditional way it's hard to transfer and hard to deliver, and also hard for the different domain in our even in our design period. Yeah.
Maybe I give some supplement. Just as my team member says, I want to say maybe we could add some AI to the future buildingSMART development. Just this.
Thank you. And for the second team, Copenhagen Metro.
Yeah, keep developing more open source solutions. We like that a lot. In certain cases, as you saw today, sometimes we had to strip them and adjust them a little bit so they work for us specifically because we have certain requirements within our business that we need to fulfill. But having that open source content gives us the possibility to take that and build on that as we did before, because 60% of the work perhaps was already done by EDS. We just took that 60% and we kind of leveraged that and used that for our advantage. Otherwise, decreasing model size, that is something that we could benefit a lot, and we know that there are efforts out there translating IFC into different formats, and IFC OpenShell supports queries into JSON IFC, as far as I know, but that's a problem we're encountering because our models are getting pretty heavy and we are in conceptual design right now. So that's something we could really benefit from. And yeah, that's pretty much it.
All right, that's great. Thank you very much. We did just have the time for the one question there, so thank you for your answers. Thank you, of course, for your presentations. That is the end of this session. So thank you all for your attendance. I would assume that most of the people in the room here are attending the dinner this evening. If you are, then be reminded that there are shuttles leaving from 6 o'clock at the front of the hotel. Last shuttle leaves at 6:30.